a sine wave modulated by a sine wave. Now, think about this for a second. If I have a sawtooth waveform, I have a sine wave. I'm doing complex FM, meaning that this control oscillator is in the audio waveform. If this is a sawtooth, remember what's in the sawtooth. We have the fundamental, we had the second partial at half the amplitude, we had the third partial at the third amplitude, so forth, so forth. So each of these overtones, these partials that are present in my sawtooth waveform, if we want to calculate the modulation index, or what sidebands are going to be created, we would have to calculate, add and subtract the sine wave to each of these overtones as well. So we would calculate how many sidebands would be created around the fundamental. We would have to do the same thing for each overtone. So if I have a sawtooth as my carrier and I do complex FM, I'm creating many, many, many more sidebands. So let's hear what that sounds like. So here is a sine wave modulating a sine wave. So now we're getting a limited number of sidebands created because it's only going to be the number that our modulation index creates given the amplitude that we set here. If I increase the amplitude, I get more sidebands. So I can get quite a few, but what happens if I turn this to a sawtooth? So now I'm getting a sideband, I'm getting that number of sidebands created off every single partial of my sawtooth waveform. So let me go back to there's the sawtooth by itself. So now as I start to increase the amplitude of my control oscillator, you start to hear a very rich sound emerge. There are so many sidebands that they're not in frequency relationships. You can get what's called very noisy sound. So as I really increase the amplitude here, I'm increasing the number of sidebands that I'm generating. So when you get a lot of these and you get very non-low ratio partial relationships, you get something which approaches noise, as we refer to it. Noise is the presence of a large number of frequencies spread out through the spectrum. So we're almost losing the fundamental frequency because we're generating so many sidebands. So that's one example. If I take this further into what's called nth ordered frequency modulation, I then take my oscillator 2, make it a sawtooth waveform, and then we have to calculate each of those partials and their sidebands generated off that, and you can see it just gets exponentially more complicated. And now we're totally into noise. We've almost lost any kind of fundamental frequency pitch sound. So if you, here again, this is good for us. If we were trying to create the sound of a cymbal, we're getting close to a percussion sound. Because when you think about what is a percussion instrument, if you analyze the sound of percussion instruments, it's a lot of frequencies present in snare drum, bass drums, non-pitched percussion. When you hit those, you're not getting a single frequency. You're getting a lot of frequencies produced simultaneously. And we would simulate that or synthesize that by using very rich, complex FM arrangements with a lot of amplitude, would start to give us different kind of noise qualities which could approximate the sound of a percussion. Now, the other thing about percussion, if we wanted to make an envelope for percussion, we've got a sound source which is very noisy here, but how would I set up my envelope generator to create the sound of a percussion? Remember, my envelope generator, if we set this up on a sharp attack and then maybe a quick decay all the way down to 0. So if we want the sound of a cymbal or a percussion, we would come to our envelope generator, a very sharp attack, and a sustained level here, and then a very quick, let's see if I can find something. Maybe a little bit more attack. So now we're starting to get the sound of a percussion by shaping the envelope onto that. So you can start to see what synthesis is the ability to shape the origination, the oscillator, to modulate that oscillator to create all sorts of spectral possibilities, to add LFOs, which can then give us the simple modulation of frequency and amplitude changes, which would give us the vibrato, the siren effects, the various kinds of things that we can hear slowly happening. The filter allows us then to change the sound over time through timbre modulation, because we can then start to have sound which is not fixed in its timbral content, but is changing through time. And then the envelope generator allows us to give us some time variance to the way the parameter of sound. When you think about what's happening in wind instruments, for example, like saxophone, the sound starts out with some amount of frequency spectrum. As the saxophone player gets softer, as the real player tries to diminish in volume, what you don't realize is the sound is actually changing spectrum also. Because as a saxophone player puts less air into the instrument, it's not just that that particular timbre is getting softer. What's happening is the instrument is getting softer, but the timbre is reducing its high partial content at the same time. So if we were to try to synthesize or resynthesize a sound of a saxophone, we would have to have some control over the volume of the instrument, but also as the volume goes down, we need to have the timbre change with it. So that way we would have a cutoff frequency filter that maybe would be changing that at the same time we'd be changing the volume. So you can start to see how sound acoustically has all these time variant variables in it that we need to really be able to control in our synthesis patch. So that's why when you really do a really good synthesis patch that has a very interesting quality to it, there has to be a lot of different changes happening throughout the beginning of the sound. One final example on that, when engineers and sound designers first started to try to synthesize the sound of a piano, and they analyzed the sound of a Steinway grand piano, and they could try to create the spectrum which matches that spectrum of the Steinway. They were very close to the sound of the piano. They would set up the envelope generator to have a sharp attack, and they would have a decay that would come down pretty slowly as it would start to decay in sound. But as they kept getting closer to it, they realized it still did not quite sound like a real piano. And what they discovered was that we don't realize that when a piano, how it makes a sound, I mentioned before, when the hammer strikes the string, the very first few milliseconds of that sound is noise. It's percussion. And so there's a percussive quality of sound to an instrument that we don't notice because it's in the first 10 to 20 milliseconds. When the string finally stabilizes and starts to vibrate, then we hear the sound of the resonance of the piano. We hear the pitch. But in that first 20 milliseconds, before the pitch stabilizes, there is a random noise quality of sound. So what they did is, in synthesizing the sound of piano, they would put in a noise generator to get, or a very complex FM, to generate noise in the first 20 milliseconds, make a very short envelope to that so that you don't notice it, but then have the piano sound emerge from that. And then it started to sound much more like a real natural piano, because there's so much going on in sound that we don't always detect what makes it sound acoustically interesting. So we'll come back to this and maybe explore some more possibilities of how we can synthesize sound with other kind of software, but this is the nature for how synthesis works.
The preceding program is copyrighted by Emory University.